We left off in the previous example of scheduling programming for a television station. And in this example, we had a one-sided left alternative hypothesis, and it was that the average number of seconds for a TV commercial was less than 30. We sampled 26 commercials. We got a sample average of 28.4, and we constructed a test statistic of minus 1.67. And what we did is we converted the 28.4, which was our sample mean, to minus 1.67, which is a test statistic that describes the location of our sample relative to the center if the null hypothesis were true. So our sample, you can loosely interpret it as being 1.67 standard error smaller than than the null hypothesis, which is fairly far away. And so if you look at this graph here, you can see that when we have a normally distributed test statistic, it's outside the red area, so it's in this blue area, which means we reject the null at the 95% confidence level. And I describe it on this slide as supporting the alternative. You can probably be better served by framing it as rejecting the null, but they are essentially saying the same thing. Okay, so up until this point, we have just used the normal distribution to motivate our analysis. And that's because the normal distribution is a very powerful model of probability that we use from Stats 1, and it is something that we want to base our intuition on. There is a large assumption made when we do this, and that's that the standard deviation of the population is known. So whatever standard deviation we calculate with our sample, when we use the normal distribution to test our hypothesis, we're assuming actually that that sample standard deviation is representative of the population. And that should seem a little bit funky to us, because if we knew what the population standard deviation was, you might think we would also know what the mean is, because it seems like we would use the mean to calculate the standard deviation. And so in reality, we don't know what the population standard deviation is. All we have is information from the sample, and so we actually have to be more conservative when we test our hypothesis, and we have to base our analysis on the sample size. And we're going to have a solution for that here in a minute called t-distributions. The other assumption that we've made so far when we're testing a hypothesis is actually just that we are testing a hypothesis. Fortunately for us in statistics too, we don't have enough quote experience testing hypotheses to really want to do anything else. But as you become more versed in statistics, you'll be tempted to manipulate your hypothesis potentially to achieve a statistically significant result, and that could be problematic. So we want to avoid doing that. But let's go back to this first comment about t-distributions, and this is what we're going to use when the population standard deviation is unknown. And just think about real life. So when you get out of UWG and you start a business, all you're going to know about your customers is the data that you obtain when they come into the store and make purchases. So you won't know what the standard deviation is in advance. You won't know what the sample mean is in advance. All you're going to do is collect the data and then produce some descriptive statistics. And that's all you're going to know, but you still may have some opinions about which products to sell or how much revenue you're going to achieve in a month. So you may still want to test a hypothesis, and you're going to want to use that data. So when we have this problem, we use what are called t-distributions to generate our critical values. we can no longer use the normal distribution, but the nice thing is that the t-distributions are also going to be symmetric, they're going to be bell-shaped, and as we have even just a fairly large sample, it's going to be, for all practical purposes, very, very close to the normal distribution. But we're going to use a different distribution for every sample size that we have. And we're going to use a different set of critical values for each sample size that we have. So if we have n observations in our sample, we'll use a t-distribution with n minus 1, what are called degrees of freedom. These are the numbers of values in a calculation of a statistic that are allowed to vary. We're going to use a distribution with n minus 1 degrees of freedom. So let's have a look at just what that means for us. We're going to go into CourseSten here, and I'm going to pull up under our content, under the tables and handouts, I'm going to pull up a t-table. We're just going to download this table, and then we'll open it right up here. This is the t-table. And you can see it's a large, phenomenal table of critical values. Look at all these critical values. That's just great. Now, have a look at the left-hand side of the t-table. You can see that it goes from 1 all the way to 30 in sequence, and then it goes up by 10 to 100, and then it goes to infinity. The left-hand side, the far left-hand side of the t-table is the degrees of freedom. It is our sample size minus 1. So as we just escape out of this here. We'll go zoom out just a little bit here. You can see that small samples correspond to larger critical values. So when we have a very, very small sample size, the numbers are bigger up here than they are down here. Okay, so how do we use the t-table to get critical values? These critical values are going to be what we use to test the hypothesis. And we go to the top of the t-table where it says confidence level two-sided hypotheses. And you can see that right here. Confidence level two-sided hypotheses. Count with me, 1, 2, 3, 4, 5. The fifth column is the 90% critical values. The sixth column is the 95. The eighth column is the 99. So columns 5, 6, and 8 are the critical values we use for two-sided hypotheses. So let's try it out. Let's suppose we have 30 observations in our data set. What we do is we go to row 29. Okay. The rows correspond to observations minus 1. The columns correspond to confidence levels that we want. We change our critical values depending on whether we have a two-sided hypothesis or a one-sided hypothesis. So we have two-sided. 90, 95, 99, columns 5, 6, and 8 respectively. We're in row 29, 30 minus 1. Here's column 5, our one-sided value, or our two-sided rather, value is 1.699. Compare that previously to 1.65, which is what we used with the normal distribution. It's a little bit bigger. Our 95% value, which was in column 6, is 2.045. Compare it with 1.96, a little bit larger. Look at column 8, that's where the 99% critical value is, and you can see it's 2.757, a little bit larger than 2.58. So column 5, column 6, and column 8 correspond to 90, 95, and 99 respectively for two-sided hypotheses, And you can see that they're a little bit larger than the normal distribution, so we're a little bit less aggressive about rejecting the null. Now, as we scroll down the t-table, you can see that these critical values for each of the columns of interest start to fall. And when we get to row infinity, you can see 1.645, 1.96, 2.576. Those are the same critical values that we used before, just a larger level of precision. Okay, now let's look at the one-sided hypotheses. How do I know whether it's two-sided or one-sided? I look for the context clues in the problem. How do I know whether it's two-sided or one-sided on the t-table? Well, it says two-sided for the two-sided. That's the big tip. And it says one-sided for the one-sided. Another huge tip. So we go to column 3 for the one-sided, column 5, and column 7. And these one-sided values are going to be smaller than two-sided values like before. So if we had, say, 20 observations and we were going to do a one-sided hypothesis, we would go to row 19, where we find 1.32 or 8 in column 3, 1.729 in column 5, and 2.54 in column 7. And we would compare those with 1.28, 1.65, 2.33. They are larger. They are larger. So as we have fewer observations, the critical values become larger, and it becomes a little bit more challenging to reject a null. That's by design because it's actually a little bit more probable to get these test statistics that are further away from the null. Okay, so let's close out of that. And let's reopen our slides here. So the goal of the t-distributions is to just be a little bit less aggressive about rejecting the null. And this is important because if we're over-rejecting the null, we may be ruling out perfectly plausible population means. And if you think of the goal of testing a hypothesis, it's to use the data to figure out which of two possibilities is more likely. We're not doing a good job of that if we don't weigh the evidence correctly. Okay, so we have more examples of how to use a t-table on this slide. I'm not going to reiterate that. I just want to point out that the one-sided critical values are larger than what we used for the normal distribution. They're not that much larger, but they're a little bit larger. So for the most part, it won't matter too much whether you use the t-table or z-scores to reject a hypothesis, but there are some instances where you would not reject with a t-distribution. Let me point out to you on this graph kind of the differences between the t-distribution and the normal distribution. Here we have degrees of freedom of 1. That means we have just 2 observations in our data set. Take a look at this red line right here. You can see that the x-axis represents, I should have written it on here, but it represents a range of test statistics. And what I want to point out from this graph is that there's still some area underneath the red line for test statistics of 3, 4, 5, and 6. So it is possible to get large test statistics in either direction. That probability goes down a little bit if we have just one more observation. You can see the blue line corresponds to 3 observations, degrees of freedom of 2. And if we just, let me pull up this t-table really quickly here. If we pull up the t-table, you can see that here's a degree of freedom of 1, and that corresponds to 2 observations. These critical values are just massive. So it requires a test statistic of like 7 to reject the null at even the 90%. But as you add even one more observation, that goes down. You can see that back here on this graph, this gap between the red line and the blue line. And if we have the yellow, it's kind of hard to see, but if you have the yellow line, and this corresponds to degrees of freedom of 10, 11 observations, you can see that the critical values fall sharply here. The black line represents the normal distribution. So you can see that the yellow sort of mirrors the black, and so as we have larger sample sizes, we won't necessarily need to worry about using the t-distribution versus the normal distribution. But as we have smaller sample sizes, it will start to matter. So when you guys take business research or some other class where you have to collect samples, one of the reasons why you have to collect a bunch of survey data is because we generally don't like to mess around too much with the t-distribution. We would like to use the normal distribution. Okay, so here's an example. Small business childcare costs. So suppose you're running a business and you're trying to be super nice to your employees, so you offer a childcare subsidy. The problem is you don't know what your employees spend on childcare. So perhaps you believe that employees spend $193 a week on childcare, and you want to do a two-sided hypothesis. So it interviews 10 employees, and here's what it finds. Let's go to Excel. It finds that employees spend $207, $192, $197, $195, $205, $201, $191, $199, $195, and $204. So this is the data. They interview, how much do you spend on childcare a week? They tell us. The null is 193. Now, if you look at the data, there are not very many observations below 193. Most are a little above, so we might think kind of intuitively, hey, we're going to reject the null. We still need to do a hypothesis test. What do we need? We need a sample mean. We need a sample standard deviation. And we need a sample size. And we're going to use that to make a test statistic. Our sample mean, we just take the average of the data. Here it is. Our sample standard deviation, we take the standard deviation of the data. Here it is. Our sample size is 10. Our test statistic, we take the sample minus the claim, which is 193. We divide by the standard deviation over the square root of the sample size. We get a test statistic of 3.195. Okay, this is a large test statistic. How do we compare it to critical values? We use the t-table. We go to row n minus 1, which is row 9. It's a two-sided hypothesis. 3.1955 is bigger than 1.833. We reject at the 90. It's bigger than 2.262. We'll reject at the 95, but it is not larger than 3.25. We don't reject at the 99. Now let's contrast this with what we did with the normal distribution. Okay, so here's a graph of a t-distribution with 9 degrees of freedom. And you can see the 3.95, if we just zoom in just a little bit here, you can zoom in. You see it actually just slots into the blue. Now, if we had our bell curve, if we go all the way back to these slides out here, if we had a bell curve, 3.195 would be all the way to the right, and it would be in the white. But with the t-distribution, it actually slots right in here into this blue region. So we don't reject at the 99. That is the primary difference on this lecture. So we are now looking up different critical values associated with the t-distribution. Now, Excel doesn't compute one sample test statistics that I know of, but Excel will look up the critical values for you. So if I were to use equal t inverse probability degrees of freedom, I could do 0.01, 9 degrees of freedom, and it would give me the 99% critical value. So you have to construct the test statistic by hand, but you can actually use Excel to look up any critical value you want, which is kind of neat. Okay, so this is the last example of one sample mean hypothesis test that we're doing in this class. And I don't know the extent to which any of this other stuff was covered in Stats 1, but we're going to cover as much of this as possible in Stats 2. So the first type of hypothesis test that we're going to cover is what's called paired differences and matched pairs. We're then going to proceed to two population test statistics, both pooled and with different populations, proportions, and chi-square tests. Let's take a look at paired differences and matched pairs. Now, I think this is interesting conceptually for a number of reasons, but the main one is that it may be useful to do a before and after comparison for the same person. So, if you start a new diet, or if you start a new study plan, or if you do something different in your life, you would like to evaluate whether or not it works. So there's some outcome variable of interest, and you could measure your before versus your after behavior and see if there's a statistical difference. Alternatively, you could do two separate treatments on people from the same population. So in a business setting, you could show two different people from the same group marketing campaign. You could look at a medical trial where you have two people from the same population. One person gets a treatment, the other person doesn't. You could look at a policy change. Any of these things can be analyzed with this framework. And we're going to think of the null as being about the difference between the two individuals, but they're going to be fused together into one observation. So I'll observe person A, I'll observe person B, but the observation will be A minus B's. Or I'll observe my behavior before, I'll observe my behavior after, but the observation will be the difference between after and before, or treatment and no treatment. But each observation has two pieces of information. We subtract them from each other. So for most purposes, we're going to have a null of where the mean difference is 0. Take a look at this mu. It is a difference between two groups, and we're only going to use 0 in this class. The test statistic, I have the sample after, I have the sample before, and I just take the difference. So this is the mean difference after, before, treatment, no treatment, policy, no policy, campaign A, campaign B. I'm just doing a difference there, and I'm comparing it to 0. There's a standard deviation in the bottom, and there's the square root of the sample size. Okay. Let's look at an example of marketing survey. So you track consumer purchases for viewing two different commercials. One has a positive attitude, the other is just totally dedicated to the COVID-19 pandemic, so it's super demoralizing. Nonetheless, you believe that there's no difference between the two with regard to spending amounts. But then you actually look. So you show people from the same group, maybe it's College of Business juniors, maybe it's your parents, who knows, 23 differences in spending. Based on, I saw this commercial and I spent this much, I saw this commercial and I spent that much. We find that consumers spend $43.23 more on the positive commercials with standard deviation of 57.43. So the first thing we want to do is just identify what the null and alternative is. Then we want to set up a test statistic. Let's take a look at the null and alternative. We believe there is no difference. Not is a context clue. So no difference. I have a not equal sign because the alternative always has some type of inequality, and the null always has an equal sign. So HA, the difference is not 0. Okay? The null is that it is 0. So null, the positive attitude is the same as the COVID-19 commercials. If it's not in the null, it's either on this side, positive is less, or this side, positive is more. But we established the 0 from the problem. The x-axis is just the spending of positive campaign minus the spending on COVID-19. So the x-axis measures two different people, it subtracts the COVID-19 from the positive, so you get one number. Okay, so you track purchases for two different commercials. You construct the 23 differences. Here's the alternative. Here's the null. Here's how we find the test statistic. The difference between the positive and the COVID-19 is 4323. This should say COVID-19. I just kind of assumed everybody thought it was negative. 4323 is the difference. Now, that could be framed as $80 minus 36.77. That would get us 43.23. You may have two numbers there and have to construct this 43.23. You may not. The standard deviation is 57.43. There's just one, and the sample size is 23. So we have a test statistic of 3.61. My sample size is 23. I go to the t-table to look up the critical values. Let's say I do that. I would go to row 22. Two-sided, 1.717, 2.074, 2.819. 3.61 is bigger than all of them, so I reject the null. I could also use Excel to do this. Okay, so I can go back to Excel and use data analysis, t-test, paired two-sample for means. Now, under the data, you should have a data analysis. If you don't, go to the file options add-ins, you can add it in. But let's say I do a paired two-sample for means. It's going to pull up this dialog. Okay, now let's try it out. Here I made up some before and after ACT prep score data. So you take a class to study for the ACT, and we look to see whether or not you do better. Okay, so let's put the before over here, the after over here, difference is right here. The before, we have this data. This is the before. Here's the after. Now, what you can't do with the match pairs is you can't mix and match the columns. This is like one person. I can't mix this person with that person, etc. Each row is its own individual. This is the difference. We can see here. If I take it as after minus before, that might be more helpful for framing. I just copy it all the way down. Okay, now this is the average before. This is the average after. This is the average of the differences. And you can see that if I take this column and subtract this column, I'll get this one. The standard deviation needs to be right down here. And the sample size is 11. So the test statistic, if I were to compute it by hand, would be sample difference minus 0 divided by square root of the standard deviation divided by the square root of the sample size. This is the t-stat I would get. Excel will produce this for us. So if I go to the data analysis paired two sample for means, all I have to do is variable 1 is the before, or we could even have it as the after. Variable 2 is the before. Just click it. You can see how E is the after, D is the before. The hypothesized difference between the groups is 0. There are labels. Alpha is the confidence that you want. You just hit OK. Alert. And here's the test statistic that we had previously. Here are the mean differences. I want to point out that Excel gives us two-sided and one-sided critical values. It also produces some p-values. So this is how Excel does this hypothesis, which is super useful for us. So if you have the data, just type it into Excel, identify your variable ranges, and it will test the hypothesis for you. When I'm doing a problem, how do I recognize its matched pairs? I have two groups. I have one standard deviation.